Huh? That's okay, man. I like that.
Okay. Bismillah ar-Rahman ar-Rahim. This is Mr. Yakubu, and he's going today to defend his work, his thesis of titled phase separation in aqueous organic nanodroplets. Okay, so Bismillah, can you start?
Bismillah ar-Rahman ar-Rahim. I welcome all of you, professors and distinguished audience, to my thesis presentation on the topic phase separation in aqueous organic nanodroplets. The synopsis of our presentation starts with the objective, the introduction, where we shall see the motivation of the work. We discuss the problem statement, the literature review in brief. We discuss the methodology, and then we discuss the results we obtained, and we conclude and make some recommendations.
With the light, turn off the light.
First of all,
Close the door here.
the objective. Our main objective in this work is to investigate the structures and the properties of organic nanodroplets. Especially in particular, we put emphasis on the water-butanol binary mixture, and we use molecular dynamics simulations at low temperatures. Our motivation. Actually, there are a number of motivating factors that make us to study this problem. The work has application in the fields of atmospheric science, cloud science, and aerosol science. And this also is another crucial area where the work has application, that is in the natural gas processing industry. As we all know, natural gas is composed of many hydrocarbons, organic compounds, having various domestic and industrial significance. The conventional means of the separation present is having some shortcomings. One, it is costly. Two, it involves use of chemicals, and it requires high-skilled workforce, and it's also having movable parts because of its heavy nature. So a recent and efficient technology emerges, that is the use of supersonic separation technology. In the supersonic separation technology, one is light, and two, it has efficiency higher than the conventional means. What happens in the supersonic process is, here we have an expansion chamber where the gas is cooled. In the cooling process, some droplets are formed, so there is droplet formation and growth. The condensates generated in this expansion chamber are then separated here, are collected in the cyclonic chamber, and then the gas passes through a diffuser for compression. And then the whole process is repeated time and again. So the formation of the droplets and the growth here motivates us to study the structures and the properties of these droplets for efficient separation of the natural gas. Now the problem. Here is where the problem comes. We based our work based on the density functional theory studies conducted by Willemski and his team. They studied water alcoholic nanodroplets, and their studies revealed two distinct structures. They observed a well-mixed structure and a cochal structure, depending on the metastable vapor state. And they found a region, one strange phenomena between the two structures. They found a bistructural region, a region in which the cochal structure can exist, and at the same time, the well-mixed structure can exist. And it exists such that for a constant water concentration, for instance, when you take 1.5, when they start to increase the concentration of the alcohol, they keep seeing the cochal structure up to the end of the region. And at the same concentration, when they start from the well-mixed region, and they come down to the bistructural end or line of the bistructural region, at the same concentration of the water, they then found only well-mixed region, meaning that the two structures exist at the same region. they exist with the same probability. We actually disagree with them in this regard. We assume that this may be due to some limitations of the method they employ, that's the DFT, using spherical coordinates, and we shall see this in more detail in our upcoming slides. Since they use DFT, and we agree that the limitation of the DFT is that it only produces structures in spherical coordinates, and we know that when we have a sphere, from the center of sphere, whichever angle you look, it will give you the same it will give you some structure due to the symmetricity of the sphere. So this MD simulation is a technique that was used by Fawaz and Willemsky. They solved for, even though they solved for water and nonane is alkane, they observed this structure, they call it Russian doll structure. This is non-spherical structure. So we feel that since this process can solve problem and gives non-spherical structure, so let us apply this method, MD simulation, to the initial problem solved by the DFT and see whether we can overcome this discrepancy. For MD simulations, the potential employed is the Lennard-Jones potential with the energy and the size parameters adjusted. We adjusted them such that they will produce experimentally observed mutual binary solubility and other macroscopic quantities. Epsilon here is the strength of the interaction between the atoms and the molecules, and sigma is the distance at which the interatomic potential energy between the atoms is 0. And then the force was derived from taking the negative of the gradient of the potential, and then the equation of motion that describes the instantaneous position of the molecules is the Newton's second law. Now the Fahd algorithm. This is just an equation that predicts the position of the atoms at any time, knowing its present position and acceleration, and having information about its previous position. At the previous time, we know its position, and we know its position and acceleration at present time. Then we can use this equation to predict its future position. We can see only position and acceleration parameters here. The acceleration can be derived, of course, from the force of F over M over A, and the force we know we can find it by taking the gradient of the potential, and we have Lennard-Jones potential as our potential. Okay. Now the methodology of executing our simulation. We use GROMATS to make our studies, and this GROMATS is just an application. It's an advanced molecular dynamics application package, has been used by pharmaceutical industries to study proteins. So we employ it, has been used long ago since 1960. So we employ it to study the molecular dynamics simulation. This is how the algorithm goes. Initially, we pack the molecules, we initiate the structures. We pack the molecules using pack-mol algorithm. The pack-mol also is just an algorithm that can create structures in form of PDB or GRO files. This is just a text file, but in our case, we even have only emphasis on the GRO file since we are using GROMATS. Now, after initiating the structures, this pack-mol can only settle the structures in a box at random. Some of the structures will be too close to each other, while some of the structures will be far away from each other. So sometimes there could be very high repulsive forces. There is need to reconcile those structures, make them aligned. So we need to reconcile the structures with the force parameters at initial temperature before heating the system. Then after reconciling the structure with the force field, and then we heat the system to about 30 Kelvin so that the system will have some velocity and energy. And then we make sure that our system is stable. We make equilibration, and then we apply our canonical molecular dynamics. In our own case, we use NVT. Now, after performing the simulations for like 100 nanoseconds, it's a very long time, 100 nanoseconds. We collect our data, and then we make analysis. We study the structures. We then calculate the macroscopic observables, such as the surface tension, the solubility, and the likes. Now, having designed our system and agreed that our system is okay, we feel that we should study also the pure butanol itself to confirm that what we have in our system is really a butanol. How do we do that? Is we execute only the simulation only on the butanol compound, and then we study the properties, the surface tension of the butanol, and then the equilibrium density of the liquid butanol, and compare it with those in the literature. If they agree, then we know we are really dealing with the butanol, since it is just a model. This is the butanol inside a box. Along this is the z-axis, and then we have x and y. Now let us see the file to confirm whether it exists. This is the density profile plotted. This is the z-axis, LZ. We can see that, like we have in the box, from the zero initial interface up to the center of the box, the density is 0, meaning that there is no butanol here, and also the last part of the box. So this confirms us that yes, our butanol exists at 250 Kelvin temperature. Throughout these studies of the structures, we use 250 Kelvin, the reference temperature for the Dept studies. This is the surface tension that we calculated for the pure butanol. The surface tension, you can see the red circles are the experimental findings, while with the reference, stated reference, and the black squares are our MD findings. We can see that we are in very good agreement with the experimental findings. In fact, this is acceptable model for water as at present. So we can see the difference between this experimentally observed and molecular dynamics finding at 275 Kelvin, almost around 10. That's the difference. If you take the difference, it's almost 10, and still acceptable now in the literature. And we can see, of course, our difference is much less than that. So which shows that our simulation, of course, is fantastic in this regard. Now the liquid butanol equilibrium density. Also the equilibrium density, we can see that they agree with the experimental findings. This is also acceptable result. Now we have studied the pure butanol, and we found out that the system contains, of course, the good molecules we want. We then went ahead to study the solubility of the mixture, to study the degree to which the water will penetrate into the butanol layer, and study the degree to which the butanol will penetrate into the water layer. How do we do that? First of all, we construct our initial structure in form of a slab with the water sandwiched between the two butanol layers. We use 1,000 water molecules here. We use 2,500 butanol molecules, and then we use 295 Kelvin temperature. Why we use this temperature, not the reference temperature for the DFT, is these solubility values that we have them for the work conducted at 295 Kelvin. So we change our temperature to 295 so that we compare our results to see whether or not they agree. Now, after making this initial configuration, using the Pac-Mol algorithm, as we've seen earlier, we allow the simulation of 100 nanoseconds, which can take almost 2 weeks before we finish this thing. This is the final configuration. You can see this water has now penetrated into the butanol layer, and also the butanol has, to some degree, to some extent, penetrated into the water-rich layer. And then we use this to calculate, to find the density profile, and using the density profile, we calculate the solubility. Like we have seen here, we have seen the penetration of the butanol into the water, So this density profile, that is what it is depicting. This is the butanol-rich region. This also is the butanol-rich region, and the water-rich cores at the center. So we can see the water has penetrated up to this thickness into the butanol, and also in this regard. And the butanol also has penetrated into the water to some degree. We use these equations to calculate the solubility using the bulk density of the water and the butanol. We find the solubility of the water in butanol, and we found the solubility of butanol in water using these two equations as the case may be. Now, the solubility values. Experimentally, it is found that 20.1%, the solubility of the water in the butanol layer is about 20.1%. However, our work revealed 17.2%. And for the butanol in water, the experimental value is 7.7%, and our MD result is about 11.4%. These are also very good acceptable values. Okay, now we have studied the pure butanol. We have also studied the solubility of, we have understood that the pure butanol now is a good model, and the solubility of the mixtures are also in good agreement as experimental values, because this is just a pseudo system, that is a model. Then we went ahead to study the nanodroplets. This is where our studies starts. Initially, we just calculated macroscopic observables and what are the quantities we need, solubility, surface tension, and others. Now, this is where we start the studies of the structures. In the studies of the structures, we configured our system such that a water-rich core is at the center, enshrined by a butanol layer. We use various concentrations of the butanol. We use low concentration. For this low concentration, we use 200 butanol molecules. For this intermediate concentration, we use 1,000 molecules, and for the high concentration, we use 3,000 molecules. This is just a cross-section view to enable you to see what is inside the molecules. And then after packing the molecules in this form, we went ahead to apply our dynamical molecular dynamics to the system. And we found some results as follows. 1. For the low butanol concentration, this is the structure that I've just shown for the low butanol concentration. After 100 nanoseconds, this is the result we obtained. A core-shell structure. A structure that contains a water-rich core at the center, and then enshrined by a thin butanol layer. This structure is also one of the structures found in the Dept studies. So here we agree with each other. Also for the high butanol concentration, after applying the canonical molecular dynamics for the high butanol concentration, after 100 nanoseconds, we found out that this, our mixture, the binary mixture, have only mixed the two components, the butanol and the water, have mixed comprehensively with each other. That is, we have a well-mixed, this is the name of the structure, well-mixed structure. These were all found in the previous work, the work of Willemski and his team. So up to this extent, we agree with each other. And this is where the difference comes. Now for the intermediate butanol concentration, we found a distinct and new structure that has never been found before. This is an entirely new structure. The structure exists such that there is a nearly spherical water-rich core at one end, and then enshrined by a convex lens of water butanol well mixed, and then coated. This lens on sphere structure is then coated by a thin layer of butanol from the top. This is just a cartoon to make you appreciate the structure. This is the nearly spherical water-rich core, enshrined by a convex lens of water butanol well mixed, and then coated on top by thin layer of butanol shell. We name this structure ourselves. We name it Russian doll shell structure, RDS. Maybe you will see it online after our work is published first. And before we go to the explanation of our differences, the work of Dept and the work of our MD work, let us go through the local number density map and see some distribution of the local density of the species. This is just the figure you can see is the local number density map, the distribution of the local density of the species around a symmetry axis passing through the center of the rich layers of water and butanol. For the water-rich core, you can observe n, small n here is just a number density. You can see the green, the orange and the red here are regions of high density. And like you've seen in the previous figure, this is where the water is dominating. So you will see here, the water here is more dense here and it's like less dense in this area where the butanol is dominating. So this is the water-rich core. And for the butanol-rich lens also, you can see for this point that the water is less here. The butanol-rich core is also dense here. This is the layer of the convex lens of the butanol well mixed, and then it is also less dense in this region. There is that thin shell that I mentioned, thin coated butanol shell here. The Dept could not show it. The Dept tried to show it, but because of its limitations, the Dept could not show. This is what the Dept, this non-flat top that you see, is the Dept trying to show this layer, but because of the limitation of the Dept could not show this region. But we are lucky actually for our MD. For our MD, we are lucky enough we were able to see this thin layer of the butanol. The small end is the number density, like I said. Okay, now we have seen the number density and the distribution. Let us explain exactly what happened. What is the difference between our work, their work, and where they got it non-tried. Let me recap. I said for the Dept studies, they had two structures, well mixed, and the core shell, and in between the two structures, they observed a bistructural region, a region in which both the two structures can exist in the same region with the same probability, which we disagree. That is what they recap. And now this is the structure we obtained for the intermediate concentration. That is where they found their binary, the bistructural region, the region in which both the two structures can exist. This is the structure we found. That is our newly discovered RDS structure. Now, the Dept used spherical coordinates. And you know, for a sphere, when you start at the center of the sphere and you look at any side of the sphere, because of the nature of the symmetricity of the sphere, you will see the same thing. It's not like cylindrical and other coordinates. So the Dept, they used mean field approximation. It just approximates the structure, and from wherever they start observing the structure, they will observe the same thing. For the first case, where they start measurements from the core shell region and they keep seeing the core shell up to the end of the binary region, this is what they have observed. The Dept was only able to show them this direction. They were only able to observe this region. That is what they found. And then when they start their measurement from the region of high concentration of the butanol, they were only able to observe this region. So they thought that this is a region in which two structures exist. And of course, it's not two structures, it's one structure, the RDS structure, but you can see the structure is composed of nearly like core shell structure, well-mixed structure, and thin shell. So they assume it to be by a bistructural region, which is actually not the bistructural region, it's RDS structure. Why they get this problem? There are many reasons could lead to this. One, they take a mean field approximation in their Yakubu potential. They use Yakubu potential in solving their DFT. So they take mean field approximation. Taking mean field means the whole structure is taken as they just approximate the structure. They will not study what differently from the other region. We just approximate the structure and observe it like that. That is the one shortcoming of taking the main field approximation in the power potential. That would be the reason for their discrepancy. Okay, now we discovered a newly RDS structure. We need to study its stability with temperature. This is at 250, the corresponding temperature for the DFT studies. We keep increasing the temperature, and with temperature, this RDS structures, as we name it, is transforming towards the well-mixed structure. And of course, at 295 Kelvin, we found out that the whole structure, RDS structure, has transformed into well-mixed structure, which means our newly discovered structure, the RDS structure, is not stable at high temperature. Now we make some conclusions, important conclusions. Firstly, we are successful in designing a model for the water butanol system, and we have computed its macroscopic properties, and we studied its structures. And also, secondly, for the spherical structures that we studied, we were able to observe 3 distinct structures instead of the 2 found in the DFT. 2 of our structures, the core-shell structure and the well-mixed structures, which were found for low concentration and high concentration of the butanol, agree with the DFT. Therefore, these studies confirm the DFT studies in this respect. However, for intermediate butanol concentration, we discovered this Russian shell structure, as we name it, and when this was not able to be, they were not able to discover this RDS in the DFT studies. So we conclude that our MD simulation disagrees. It disagrees with the DFT studies in the region, in the bistructural region observation, because we observe a new and distinct structure, and we attribute this discrepancy to their DFT limitations. And then we make some recommendations. Firstly, these studies, we conducted it for water and butanol system. There are other higher organic hydrocarbons that could exist in the natural gas mixture. So it will be paramount to study such also compounds, how they mix with the water, and even within themselves. Perhaps we could discover another new structures, or explore other thermodynamic properties. And also for the parameters we used. For the water, there is no problem. It has been extensively studied. People have done so much work there. So there is a standard acceptable model, it's SPCE model for the water. That is the energy parameters used in the Lennard-Jones potential. But for the butanol, however, there has not been much work in the field. So there is still need for extensive and further investigation. We use a tri-P model for the butanol. There are many kind of models, OPLS model, tri-P model, but still needs to be further investigated. We use tri-P model in our own case. And then also, we give another recommendation that there is a need to study these structures and make these studies at extreme high and extreme low temperatures and see what happens. Another important recommendation is this our RDS structure that we discovered. It will be essential if we confirm, if further studies confirms that this newly discovered structure is really a critical nuclei, because only those critical nuclei are essential, only those are relevant in the nucleation process that takes place in the supersonic nozzle, like we mentioned, the area of application of this work. Having completely successfully finished our work, we have to give some acknowledgements. First of all, I have to thank Almighty Allah subhanahu wa ta'ala for making this work a success, for making it a reality, and for sparing our lives good health and wealth to study this problem and solve it. Alhamdulillah, secondly, to my parents, I just have to pray that Allah continue to bless them, bless their lives. They have done so much for the right of bringing. They have done a lot of sacrifice to see that we are successful in life. To my advisor, words cannot express how grateful I am, actually. But I know Dr. Fawaz is a remarkable role model for me. He has done so much to see that this work has become a success. In fact, as I am speaking to you from Jordan, just to come and attend this event. So I am utmostly grateful, and I just have to pray that Allah shall bless you, sir, bless your family, and your end. To my committee members, at this point I want to believe, actually I'm one of the luckiest students in the department. Having this kind-hearted people, friendly people in my committee. Doctors, I'm very grateful for your positive comments, advice, and contribution in the course of doing this work. Dr. Ibrahim, whenever I went to discuss the thesis with him, he starts by giving me some sweet in his office. This is really interesting. Also, the chairman, physics department, Dr. Abdullah Shumaili, I'm grateful also to him for his fatherly advice and support in the course of doing this work. The entire faculty and staff of physics department have done so much, actually. I have benefited, I have gained a lot from their wealth of experience. I have to thank them. I'm really thankful. I'm deeply indebted to them. The Ministry of Higher Education, also Saudi Arabia, I'm deeply indebted. I thank them, and I pray that Allah shall continue to protect the kingdom and the entire world. To my mentors, you will see them. You can see their faces. Mentors, those who have been advising me since from day one in the school. Colleagues whom we have been working day and night, solving homeworks together, ups and downs. I have to thank them also for their friendly atmosphere, family and friends also. I thank all of you. And lastly, but not the least, my Nigerian community in K.F.U.P.M. This is home away from home. Actually, I'm also grateful to their services. They have done so much to us. Dr. Khalezi, thank you very much for coming. You are part of the people that I gained so much from you. Actually, take me a course. And in our midst also is one of my undergraduate lecturer, Dr. Mansur. Thank you very much, sir, for coming. You taught me chemistry, and alhamdulillah, my work is related to chemistry. So I'm proud to present to him that I'm still not, I have still not deviated from his field. Taught me organic chemistry in 100 level in Nigeria. Is there in our midst. Thank you very much. Alhamdulillah.
No question. Sorry? No question. After this acknowledgement, okay. So, Dr. Ibrahim Nasser?
I will tell you my comments.
From the audience, any question?
We start with the members.
Okay.
Okay, and Dr. Abdullah?
Dr. Ibrahim, you want to start?
He said,
Okay, I have just small questions. 1 nanosecond was a very long time.
100.
Yeah, 100 nanoseconds. So, how long does it take the RDS structure to form? Just few nanoseconds? Or you just run it for 100 and stabilize it after that amount of time?
Okay. What we do is like, it's not like we run the simulation and we keep seeing the structure after 1 second, after 2 seconds, we see how it's.
I know, yeah.
Yeah, that's not how the work is actually. How the work is, we set the simulation time, and then we submit the work. In fact, we use a draw file at the end, MD draw file to record the structure, and the output, MD draw output, you will not find it until after the last 100 nanoseconds. That's when the structure will just evolve.
Yeah, so you don't know the time at which
The
structure appears and
Actually, you can,
stabilizes?
because we have trajectory file, TR file.
Yeah, we have TR file that like at some times, you know, you can even study the stability. Maybe after 50 nanoseconds, you study and see the properties of the structure. Maybe if it is okay for you, you can just cancel the simulation. You can exceed the time. But actually, this is the 100 nanosecond, the best time for us that we discovered this structure. It exists. We try for the lower time, but we did not get a very excellent result until at this time.
Okay, so it converges to that and not changes.
Yes, that's right.
Maybe, I remember, it's less than 15 nanoseconds, you will reach,
15.
yes, less than 15, you will reach final structure. But usually, because in MD, we use the ergodicity to average, so we average over time, because we have only one sample. So usually the MD, we don't have many samples and then find the final structure and average over the number of samples. But in MD, they usually average over time. So we're trying to reach the maximum time we can. So because of, we are limited in this HPC here with the hard disk, so we only go to 1 nanosecond, 100 nanoseconds. It's a very long time actually, 100 nanoseconds. But if I have control, maybe I can go more. Because we had time, we had long time, just we finished the simulations, but we cannot add more jobs.
Yes.
Yeah, but we averaged to make sure there is no any error bars or these things. We only average over the last 20 nanoseconds. So we consider the first 80 nanoseconds as equilibration.
Second small technical question. You all of the codes you just take and run one. Have you tried to do some of the codes yourself? Write some of the codes yourself that you have used?
Codes?
Yeah,
No,
computer codes.
We do not write any code ourselves. We do not write any code.
And did you look at the codes and how they are?
Yeah. We studied the course with the course actually. We look at them, but we did not do the code ourselves.
Okay, that's right. You can learn a lot by writing code.
We only input the parameters that we need into the code. We make some changes to make what we need, like for the regional tri-P model and other things, the energy parameters. We change so many things to our own satisfaction, but we did not touch the model language. That's right.
Okay, more questions?
That's a good thing.
Any question from the audience?
Yeah, I have, I think, something really...
Okay, we'll go back to members, okay?
Yeah, starting from the first page in the introduction, I found many abbreviation, and really I stuck with many things.
And this copy,
Yeah, I think that one is before the final correction, right?
We need
to know what they are doing. Because maybe somebody come after you and he will use what you do, and he will not get the right results because you did something wrong before. So if you know exactly what you are doing, then you can go and play inside the GROMAX. Otherwise, just leave it as.
Maybe it's a good idea to write subroutine that. Subroutine that you can change and you can embed it there.
Yes, so it's very sensitive to work inside the GROMAX. So I don't recommend this. If you do this, just do it for your copy. Don't give your copy to another people, okay?
Okay, and also there's something it looks to me very important when you talk about the Yukawa potential or all this stuff. You cannot work with spherical coordinates with the Yukawa potential for molecules. It should be another relative coordinates, parabolic coordinates, but never work with spherical coordinates. I don't know why you.
No, we actually did not do that for our own studies.
No. You
The
said
reference-
they used Yukawa and spherical coordinates, but I don't think they can use it in spherical coordinates.
Check it. Just check it out. What?
Yeah, I studied actually. I look at their work, but yeah, of course, I look at it and that's what is.
No, I don't think they say spherical coordinates. It cannot work.
R and lambda actually, right? That's what they used.
Anyway, and this should be another coordinate rather
Actually, they used spherical coordinates.
No?
They used spherical coordinates and they solved the differential equation with the Green's function. And they found it. Yes, exactly. And the paper is very famous
you
now.
have molecules and you have the interaction between the molecules. It's,
No, there. And
I see.
DFT, forget the DFT, they don't look on like particular molecules. It's just they average the structure.
Okay. خلاص.
Okay, so it's
Clear.
completely different structure.
خلاص, that's it. Thank you very much.
Any question
Thank you.
before I start asking? Yes.
Okay, I would like to congratulate my friend and colleagues for the beautiful presentation. Even though somebody whispered to me that it was a lecturing, and I said it's actually a lecturer. On slide 22.
Slide 22.
It's like, okay.
Sorry for bothering you actually. What's I believe that is you will.
Okay, it's okay.
You need to always remember MSc thesis. Why Russian and this why Russian share, why not Arab ball share structure?
Yeah, you're right. Why Russian Dutch, right?
Yes. Since you are not naming it and it's probably to be the first
Yeah, it's a
nomenclature, so why do you have to make it Russian doll?
Nigerian.
It's not natural. Actually, what happened, you see, like I said earlier, we have, I explained we have core shell. Like when you have this, you have a core of water, and then you have a shell. This is what we call, this is the shell, right? Okay, fine. Okay, yeah. Thank you. Fine. Okay, yeah. Thank you. This is a core of water, and this is a shell. So not this one. We have a shell. And we have studies conducted by Fawaz, like I mentioned. Let me go back to the slide, please. They found when they studied nonane and when they studied water and nonane is alkane, so it's not immiscible. It's not miscible with water. They found this structure and they call it Russian doll. Maybe the reason why they call it Russian doll, this is only Russian doll, our one is Russian doll shell structure. So they call it Russian doll. Maybe the reason is, if you can remember the Russian doll toy, maybe you know it. You can check Google. Yes. You will see Russian doll toy, something like this, with very small protrusion. So that's why maybe they call it, the inventor is there. They call it Russian doll structure. So our own, we have the Russian doll. Let me go to the slide 22 like you said. If you look at it, it looks more or less like this only is a Russian doll. If you look at it without this, then you have additional shell. So we just add the two and we name it Russian doll shell structure. RDS.
Okay, thank you very much. Secondly, what would be the implication of this structure in the application?
Like I said earlier, let me go back to slide 1. The application of studying this structures actually is, this is separation we are trying to intensify. We want to provide we want to give them information as to how these structures mix with water, how they separate, and all other stuff like that. So if you can know how exactly these structures interact with water, interact with themselves, and they separate at what some pressure, at whatever observable they separate and interact with each other, then this will give you information, novel information as to how you can prepare your separation process, because you are dealing with separation of natural gas components for their various domestic and industrial significance. Thank you.
Can I ask you a few questions?
Okay, thank you.
All right. Can you go back to slide 22? Same thing. Anyone? Okay. Now, which one is water, the blue or the?
W.
All right. And the temperature is?
It's 250 Kelvin.
And the freezing temperature
No,
of
this is
water?
290, I think.
No, we have the 9.
Oh, 290 is complete.
Look
Complete.
look at what you are talking about.
It's complete. Okay.
Look at the text.
Yes.
All right, let's go back to that. So, freezing temperature of water is? Freezing temperature of water is
0 degrees.
Kelvin.
In Kelvin.
0 degrees, 273.
27, okay, which means now at this temperature, water is already solid. Good. So, it's not mixed.
I think we can have water, vapor, like, not necessarily light. We can have water at less than 0 degrees, depending on what you are doing. In our own case, we say we study it at low temperatures, like like we said, the separation is based on condensation. Actually, look at here. The separation is based on expansion. When you reduce pressure from gas, of course it will cool down. Okay, like you taught us in the low temperature course, it will cool down, and there will be formation of droplets and froth. So since we are cooling the system, there will be some droplet formations. Maybe there may be some other sophisticated mechanisms that take place in the supersonic separator, but of course we did not go deep in studying what the supersonic separator is all about. It's just part of our application, but what we only care about is how the structure of them and what happens to them at this.
What I'm saying is like from basic physics, basic understanding physics. Yeah, but that temperature of water, there's a good chance that it's already in the solid phase.
Yeah.
And the butanol or whatever other compound there might be like liquid or gaseous phase. You're gonna surround whatever core you have there. So that's expected. And that is, anyway, it agrees at higher temperature. You have both of them, you're sure that they are in the phase, in the gaseous phase, or liquidous phase, or whatever it is, and they are more like uniform distributed there.
Even here, you will see the temperature is not that high. Yeah. It's not that high. Even it's just room temperature, right? It's not up to more than 25 degrees Celsius.
Yeah, but
So even this one
above.
is still not high temperature. This one is. That's how, yeah, this one. Even this one, it's not.
But it's okay, this is all right, because it's like more like water and 4 or 5 of gases there. So you have more chance of mixing. Now the other thing is in the chamber, industrial application, usually the temperature is much higher than that, right?
The temperature?
Yes.
Yeah, it's good.
Yeah, it's good. Have you tried to look at that at higher temperature? Because if you try to mimic what's going on experimentally, you have to do that at higher temperature, maybe, I don't know,
Actually,
300, 400 or...
Look at this. This is, okay, yeah. Actually, this is one of the recommendations that I give. It should be done maybe by someone, or maybe
By you.
by me next time.
Why not you?
Yeah, actually, there is one thing maybe I can add.
Okay.
Maybe only one water model can freeze molecular dynamics. I think it's newly discovered, as they call it, MW water. And it's discovered by, I think, Valeria in Utah State University. So, otherwise, it's very, very hard to freeze water in ND. Very hard. Yes, it's very, very hard. I remember with SPCE and TIP40 and TIP5P, I went less than 150 Kelvin, I couldn't get a cluster. So, but what the people are interested in.
That's maybe because of the potential that you're using.
Exactly. Yes. Potential and many other things. So, but it's fine. Okay. So another. Thank you. So no, thank you. Go to slide the bistructural region.
Slide 1.
No, to the
You know, there is
first
things outside you can.
slide by university.
Open and check.
Yeah, why not?
First,
Because if you leave, what are you going to do with it?
they are this one.
Keep you are going over there. They can take.
As you see, the people here, they control parameter in their experiment or
we
their
can take it for
PFT is the activity, right? The water vapor activity, the pendulum vapor activity. But in our simulations, we only use the concentration. So how can you like confirm we are doing the same thing?
Yeah, actually, even the activity is is also concentration. It's signifying concentration, only that pressure based. It's the pressure, like in terms of pressure, PI over P over PI. So the activity and the concentration is just like saying mass density, bulk density, whatever density.
Yeah, how can you prove that? Show me, you have the board.
In mathematically or what?
Yeah.
Prof, I don't know.
Okay. This is what. Okay, what's the definition of the vapor activity? What do you mean by vapor activity?
Vapor activity is the ratio of P pressure over the initial pressure. Actually, the pressure of the water at any point then divided by the initial pressure P over P.
Okay, so you write there A. Just write A is the activity. Small a activity. A is
P.
A is PI over PI naught, right?
PI.
P naught.
PI naught and this PI. Right. So this is the vapor. PI is the vapor pressure in the supersaturated vapor, and PI naught is the equilibrium pressure. So PI always greater than PI naught. So we go from 0 to somewhere, right? After 1. Now we have vapor, right? We have gas. So usually the gas is governed by which equation of the state?
Ideal gas.
Ideal gas. So just write what's the ideal gas?
Equation.
Yes.
Ideal gas.
Exactly. You divide by V because we have NVT. So N over V is what?
Number density.
It's the density, right? So P is proportional to the density, right? So this is how we govern our ND, because we cannot, in our ND we cannot control the pressure, but we can control the number of particles. Okay?
Yeah, that's right.
Okay, go to the solubility.
This one?
Yes. So I see here we have like water and butanol, and they mix themselves, but they are not completely mixed, right? We have some reason it's not completely mixed. The water is not, right?
Yeah, you mean here?
Yeah, but we have temperature at 295, right?
Yes.
But you showed us that when we have spherical structure, they completely mix.
For the?
For the spherical well mixed structure.
Yeah.
So this is at 295, that one is 295. But this one just partial, right?
Right.
But at 295, they completely mix.
Okay.
So why?
But the butanol number is not the same.
So what's how can you translate this?
Look at it. Okay, you mean, yeah, we have how many hours, the number of the butanol, 1,500, and there we have 3,000, I think. Yeah, also, we have 3,000 butanol molecules. And this solubility is also related to the number of the butanol concentration. Like we've seen.
No, I'm talking about not the 3,000.
Okay, which one? Okay, the last one.
The last one. This.
This is just 1,000. Even this one is not completely well mixed, actually. Look
No,
at
but
it.
it's completely well mixed.
Yeah, it's well mixed, but not like
No, it's completely
only not like the 3,000.
This is
one,
just a snapshot.
right?
So it's completely well mixed. But I mean, why this one completely well mixed? That one is still we have water rich phase, still we have butanol.
And I think that one is also.
You just answered. You said
yeah.
because of the number of butanol.
Yeah.
But explain to me how that happens.
And that could also be related to the configuration we made. This one is we made in form of space,
Yes.
like spherical structure. So the uniformity is like to be uniform, the distribution of the water in the surface of the butanol. But this one is just a slab. So definitely it will not mix like spherically symmetric structure.
So if you have only 1,000 water, you will get completely wellness.
If you have 1,000
Water.
here,
Yes.
you will not. You will not get. It will be something still similar to this. The butanol will still penetrate. The water will still penetrate the butanol layer to some degree, and then the butanol will also pass through the water to some degree. But you will not have that well mixed like the atmospherical.
This time will not answer. Okay. You have to figure out the answer.
Okay.
Okay. Okay. So maybe it's time for the audience to leave.
Audience.
Okay.
It's time to pray.
So is there Okay, there is a refreshment outside.
Job well done. Now we see this next time.
You have to take him to Bahrain next weekend.
Congratulations.
انا ما حضرتش لاي حاجه قبل كده علاش كاشاري
Final.